So each of those v's being multiplied by, it gives you sigma I ui. And this matrix sigma is the same shape as A, and indeed if you write U transpose A V, that's equal to sigma, and that means we've diagonalised the matrix A, but because it's not square, we've padded it with zeros. And I drew this in the overdetermined case, because that's the natural one to look at. Of course, you can apply the same thing to A transpose, in which case the augmented block of zeros will be up here. So, so somehow what we've done is we've changed coordinates, we've changed variables so that our images are written in terms of the v's, and then our data is written in terms of the u's, and then our forward problem is just a diagonal matrix. It just says you get smaller and smaller components. And so it's obvious that if you're only measuring, to a certain accuracy, and these singular values are much smaller, you don't have any reliable information about them. So what you could do is just assume that those components are zero, you know nothing about them, so set them to zero, and then only solve for the components, the VI's, that have big enough singular values. Okay, so how would you do that? Well, let's first look at A transpose A inverse A is sometimes called A dagger, the Moore-Penrose generalised inverse. So that's the expression that came in the least squares thing. Well, it turns out that it's very easy to work out A dagger, A transpose A inverse A transpose, using the SVD. So in fact, to do A dagger, well, let's just see. If we wanted to invert A times something, then we could change into the singular vectors and then just divide by sigma, right? So it's kind of easy to see how you do that. I can just substitute my singular value decomposition in here, but I may do that a little bit more quickly if I wrote it this way round, because that's an expression for A, isn't it? Yeah. In which case, well, maybe I'll just do this, because if you work out A transpose, that would be V sigma transpose U transpose U sigma V transpose, and then times A transpose would be and of course these U's to cancel out, and so I've got and then to invert this, and of course sigma transpose sigma is the square n by n matrix of sigma squareds. And so to invert this, of course, I just undo it by doing a V transpose first, then doing a sigma transpose inverse, and then when I finish that, doing another V. So to invert this, I do V transpose to cancel that to cancel that, and a V to cancel a V transpose, times V. Oh, well, it's transpose, not dagger. And so, so that's actually quite simple because the V transposes cancel. Which is actually just V, and then if I just sort of draw this matrix, it's just 1 over sigma 1 down to 1 over sigma n, and so let's sort of summarise what you do. You write your data in terms of the singular vectors ui, and some of them, you've actually got too many of them, you've got more than you have unknowns. Well, those components don't tell us anything about the unknowns, right? So we throw them away. That's just because we've got too many equations. So that's actually projecting onto the range of the operator, that's nothing more. So you can't get those by doing a times x, so they're definitely just error. And we just knock them off, right? So this block of zeros says just kill off all the components of u that don't even have a v to go with them. And then you divide by the singular value, which is inverting the matrix in our nice diagonal system, and then you put it back together by writing these as sums of v's. Actually, this is actually the more Penrose inverse of sigma. So this matrix is actually sigma dagger. It's just because it's diagonal, it's can be easy to calculate. Okay, so this illustrates what goes wrong. I should draw that a little bit further down. I think I know, you know what I mean, that these sigmas are 1 over sigmas in order down the diagonal. The matrix was rank n, so I'm not dividing by 0 here, but the nth one is very, very small. And so this number is enormous, and you can see that the component of un will be exaggerated. So any error in it will be massively amplified. So the easy way to do this, the truncated SVD solution, x TSVD, is just v, and you get 1 over sigma 1 down to 1 over sigma k, and then you put some zeros, and then you have a block of zeros, u transpose. Transpose not dagger, b. So the truncated SVD, what you do is you write your data in terms of the singular vectors, you throw away the ones that we really don't care about because they're orthogonal to the range, so they couldn't be real voltage measurements, and then you go down as far as some value k, divided by the singular values, and then you regard the rest as just rubbish, and you black those off as well. And so the rough idea is that when sigma k is around the size of the errors, then you say, oh, this is just rubbish, I won't include that in my picture. So k is determined by, well, you could take the first sigma that falls below your value of errors in the data. But in practice, you usually want to stop a little bit sooner than that. So that's a truncated singular value decomposition, and it's another well-known common method for solving an inverse problem. So it is actually a kind of regularization. Instead of an alpha, you choose which k to truncate at. Well, here's the thing. If you're solving a linear inverse problem, and you know exactly what measurements you're going to make, then you can work out the matrix A in advance, and it's actually quite expensive to work out the SVD. So it's sort of, for matrices of the size, 100 or so, that's easy. Kyriakos, what's the biggest matrix you've SVD'd?
30,000 by 30,000, something like that.
Really? Did you get... But
I ran out of memory.
Yeah.
One thread column.
Yeah, but the point is there's a limited version of SVD, say in MATLAB, that produces the first few singular values and doesn't bother working out these because with rounding error they be rubbish after a certain amount. But if you actually want, you know, to get U and V and the sigmas for all the matrix, then you know, modest size matrices, that's fine. And usually one-dimensional inverse problems, that's fine, but sort of three-dimensional massive systems, you kind of can't really do this. So it's useful, you know, as a tool. You can actually do this, and for small systems, it's where the matrix doesn't change, and of course in EIT it's non-linear, so we want to update the matrix. We're not going to work out the SVD of an enormous matrix and then update it and work out the SVD again. But it's a very useful theoretical tool. You look at the decay of the sigma i's, and you can mess with them in various ways. And in fact, you can say that also that X tick, the Tikhonov regularized solution, is obtained in a very similar way, that you just interfere with the singular values in a different way. And what you do is here, you replace it by sigma 1 over sigma 1 squared plus alpha squared. And so for alpha small, that's just 1 over sigma 1. Right? But when the sigmas get very small, then this, instead of dividing by a small number, you've added alpha squared, you're really just dividing by alpha squared. So it achieves a very similar result of not massively amplifying the different components, whereas it doesn't just stop them at a certain orthogonal component. But the moral of this is, if you have a system where you know the SVD, and in some cases you can calculate the SVD analytically, then you can just apply Tikhonov regularization for a whole bunch of different alphas just by changing this bit and leaving U and V fixed. So it is a useful tool in that respect. And if you look at Hansen's regularization tools and the examples in that, he usually treats one-dimensional inverse problems and he works out the SVD, and that allows him to play with the regularization in this way. Okay, so I'll stop there.